The next talk is by Jörg Arndt. And there be dragons. Thousands.
Okay, welcome. First, can you hear me well? Like that? Not so good. I try to do better. So stop me if you do not understand me. So the day before yesterday, this computer still worked. No, it doesn't. Some of you have seen. So I have to draw everything on the board. Okay, what my talk is about is basically the following. If you look into publication about plane filling or grid filling curves, it's just a few that feature over and over. For example, the Hilbert curve. Let me draw one iteration of it. Right, there you have the Hilbert curve.
That's a permanent marker, I think.
Oh, no! Oh, well, that's good. Then it's permanent.
It might still erase.
So it'll be harder.
So leave it there. Alcohol will work. You're right.
Okay.
Okay, that's the Hilbert curve. It's not the Peano curve. The Peano curve works like this. 1, 2, 3. That's the Peano curve. This features over and over again. This is Peano French title, which says about a curve that fills the whole plane. 1890, and the following year Hilbert über die stetige Abbildung einer Linie auf ein Flächenstück mathematische Annalen. 1 year later, about a continuous map from a line to a piece of the plane. Right? And yeah, I said there's lots of papers, but I'm only going to mention a few which I looked into. A recommendation around the stop would be Kosinkovic and Lindenmayer, The Algorithmic Beauty of Plants, which you can download freely from the internet. It was Springer Verlag, 1990. A classic, for my purposes, would be Chandler Davis and Donald Knuth, number representation and dragon curves. It's reprinted in his book Fun and Algorithms, I think. Fun and Games. Right. So, my goal was to generate all plane filling curves of a certain form. We all know, I guess, these are generated by a certain L system, Lindenmayer system. Who is not familiar with Lindenmayer systems? Who is not familiar with Lindenmayer systems? Okay, right. Lindenmayer systems, I write one down for you. You have an alphabet, substitution rules, and do parallel substitution. Here I write down one down for you. Alphabet would be F minus and plus. F will be mapped to F plus F minus F. Minus, let's be lazy, it's mapped to minus, it's constant. Plus will be mapped to plus, it's also constant. I'm lazy today. And then we need an axiom with which to start, right? And our axiom is F. Now we do the parallel substitution. Can you move it from here? Yes, I can. That's good. Now we do parallel substitution. Axiom is for me also generation 0. 0 is the axiom. Generation 1 is do the replacements in parallel. F is replaced by, that's German one, sorry, F plus F minus F. Second generation, okay, F is F plus F minus F. We done the first symbol here, the plus stays there. Now comes F plus F minus F. This is copied, and again F plus F minus F. Right. And that's a good reason to own a computer to do this sort of stuff. Okay? Why did I choose this? Because it describes actually another grid filling curve. Fine.
I'm drawing the curve in front of you.
So now, this is an example of a very simple L system which generates a grid filling curve. It goes like this. We interpret Fs, draw a unit stroke. We interpret plus if make a turn by 120 degrees. And a minus, make a turn by minus 120 degrees. So generation 0 would be just a unit line, right? And I have to scale now. Generation 2 would be turn scale 1, 2, 3. And now I try generation 3. I have to draw the helper here, the motive, and this would go roughly like this. This goes roughly like this. Oh no, I messed it up. Sorry. So, and the next one would go like this, this, this. And actually, it's not quite. If I tell you this is a grid filling curve, you would say hardly so, but it is, and it's well known. This guy is called by Knut Elite the terdragon, and I draw it for you here. This is actually 3 of those curves, higher order, right? And I put them together. And this whole triangular thing here is a tile, the tiles the plane. And just to show you that little variations of LSM systems do rather big things, I show you another one. Here the motive is like a small z, right? Z. And if I modify it slightly, like a capital Z, like this, let's make that very clear, this happens to give another virtual curve. And this one is shown on the back here. And to make the structure clear, here I make these colors. So this goes this way, and again this here is a tile that ties the plane, which is, by the way, the same that you get with the numeration system, complex numeration system. Okay, I flipped it. 0, digit 0, digit 1, and equal 2 complex roots of unity, and base 2, I hope, as a generalization of the unit square. So now I thought, why do we only have so few curves? I want them all. I do combinatorial generation as a hobby, and I want to generate objects of certain kinds. So you first have to reduce the search space enormously. For example, these curves, all the very well known there, the dragon there, the paperfolding dragon, are generated by L systems that have 2 non-constant symbols. For example, if you read that to me, that highway dragon goes as follows. It has plus and minus are always constant symbols. Read it to me. L goes to
L plus R,
L plus R, and R goes to
L minus R.
L minus R. Okay. And my search is only about L systems that have just 1 non-constant symbol. It seems like a pretty reduced problem, but as you will see, it is the results say otherwise. So let's see. I, for example, do not allow, you can do many things like rescaling the units, etc. I just say 1 unit length fixed turns by, I will talk about like here, allowing turns of 120 degrees. And all these objects, these curves, live on the triangle like grid, all these live on the triangle like grid. And in another search, I allow only turns of plus minus 90 degrees. In these curves, the 3 in there, they live on the square grid. So, why did I start that? I, of course, dabbled in the with pencil and paper. I did a bit of searching several years ago, randomly, and then entered Jeffrey Van Trella, 2012, and he's written a book which is called Brain-Filling Curves, a Fractal Bestiary. And he shows many fractals curves generated by slightly generalized L systems. And what I seen there, he had one that was generated by such a simple L system, just one non-constant symbol, but it was not symmetric. And I say, wow, it was exactly this curve here. I didn't know, did you know, that you can have such a simple L system and get a non-symmetric curve? I didn't know that. And so, immediately what you see, there I showed you can put 3 together and you get a tile. Here you can put 3 together in one way, getting a funny tile, or in another way, getting another tile. This coincides with Gosper's island. And he had some other curves which I have to skip for time reasons. The spectacular results are there. Maybe you have time later. All right. And just 1 month ago, I learned that William Gosper had this curve in the 1970s. Of course, he didn't tell anybody. So my plan, starting November 2013, I'm going well into Christmas, was the following. Search all curves generated by simple L systems, one non-constant symbol, only unit length strokes, and turns fixed by either 90 or 120 degrees. I skipped 60 degrees. Those curves may be and not be. This is a part of a curve, this is a part of a curve. They may not be self-crossing, that's verboten. They may not be edge contacting, that's verboten as well. But they may be corner contacting. If we forbid that, we get none. Okay? So I started to do the computation. It turns out the search space is still pretty big. And at first, the first curve that exists, they exist only for certain orders. By order, I mean the number of f's this f is mapped to. This is order 3. This is, and that would be order 4. Right? For example, for order 3, one curve exists. You've seen it. For order 4, one curve exists. You've seen it. Both are sort of well known. For order 5 and 6, no curves exist. For order 7, 3 exist. One you have seen, this is order 7, actually second, and there are 2 others. The primitive of one other goes like this. 1, 2, 3, 4, 5, 6, 7. And still another one. It goes like as follows. 1, 2, 3, 4, 5, 6, 7. And now we are at the position to define curve versus shape of the curve. These are 2 different curves. Well, this f goes to f plus, f minus, f minus, f plus, f minus, f. And this goes to f f plus, f minus, f. Different curves, but the same shape. As you see, right? The set of points, and even possibly modulo, if this is 1 point here, actually now I sort of destroy the drawings, is the same. And this is the smallest such example of different curves with the same shape. And this will be very important later because I will find in the higher orders, for example, 35,000 curves of a certain order, but only 1,800 something shapes, which I can look at. And the number of shapes of such curves on the triangular grid makes sequence A, 2, 3, 4, 4, 3, 4. And as number of shapes of grid filling curves apparent on the triangular grid closed band with turns 0 plus minus 120 degrees that are generated by Lindmeier system with just one symbol apart from the turns. Okay, now we know what it is. And here are some facts I initially did not need for the search, but later turned out to be crucial. For example, a curve, curve of order is the number of s, there, right, of order r, has squared distance, and I define it in a second, equals who r. Square distance is the distance from the initial to the last, right? And you have different sets of allowed distances on these grids. For example, on the square grid, it would be x squared plus y squared. On the triangular grid of the form x squared plus xy plus y squared. So you have some orders for which no curves exist. So then the other next thing is the net turn for the L system is 0. Right? You see on every of these examples, you see it goes in that direction, it goes out in that direction. Also here, in direction equals out direction. Another example on the square grid, I think this is also one of the few along. This one works. And you can see 5 strokes and distance condition 1 squared plus 2 squared is 5. And this actually works. It's only necessary condition. All right. Another random fact. On the square grid, we have no 0 terms. No, how do I call it? 0 terms. It's easy to convince one side that this wouldn't work, right? Okay, now we really want to have some sufficient condition. What would you do? You can always check OLL systems, it's just a trivial combinatorial generator, and then how do you check that the curve actually works? Well, necessary condition would of course be generation 2 is okay as well. Okay, meaning not self-crossing, not edge contacting, and yeah, for a second generation, that is a necessary condition. Would it be sufficient? Yeah. It's sufficient. Second generation, okay. Curve, okay. Another way to try, necessary condition, you try the first generation, but for example on the triangular grid, you put 3 of them together and check for the tile. The whole tile, tentative tile, must be not self-crossing, no double edges, and have the right area. And you do this for the other tile, flip the other way around. And of course, that is a necessary condition, and it turns out to be sufficient. Okay. So, I write both tiles are okay. Okay? And we have curve okay. Right. Now I have to admit that I don't know how to put any on this. And I'm actually ashamed about it. I guess this is well known. I didn't find it, really tried. And no. I can't prove any of this. At first, my search was exhausted, assuming nothing, and I visually checked every single curve, which I actually did till the bitter end. But then the search is inefficient enough to stop at order maybe 13 or so. Right? It's always 2 to the 13. You have to go curves, shapes, do geometry on that, and that's not computationally cheap. So, how much time have I left?
About 15 minutes.
All right. That should be okay. So, admittedly, later on, I said, okay, this is all really true. So, if curves exist, for example, where this would be wrong, then I could have missed some, but I don't think so. I'm convinced, as somebody said, it is true. Okay, so let's look at the what I've done. I just shortly tell you. It's basically first part of the engine is stupid combinatorial generator doing numbers, right? It turns plus, minus, 1, and 0, for example. Then you draw a curve, you do geometry, you check for shape equivalence, to reduce the sheer number of them. And then you get to order, say, 13, 15 on the square grid, same on the triangular grid. Then you assume this all is true, and you assume, then you just optimize away. And that, one may ask oneself, why hasn't that been done 25 years ago? And I think the answer is actually a 4-letter word, work. It's a lot of work. It was hard work. For 2 months, hard programming and even optimizing this. So I can send you the program on request, but your eyes will bleed. It's complicated, it's fast like hell, but it's very, very ugly, even with documentation. You can touch anything, the whole thing goes over. So the last searches I did was, for example, on the, let's go for the triangular grid, I did order 31, and it sort of hits the wall. I find I then have to test only 487 billion candidate curves. I find one valid curve in about 5 seconds and one new shape among those curves. Some give the same shape in 5 minutes. It's nice to watch, like watching the washing machine. The unoptimized version of the program, this one took 130 hours roughly. The unoptimized version would have taken pretty much exactly 7 years. And pretty much the same for the other grid. And the optimization, the speed up was a factor of between 200 and 800. There was a lot of work. So now, of course, I could search further, parallelize or do anything like this. But really, I don't have. The next step would be use a more intelligent algorithm. It's quite dumb to do the L system and then to look if the curve has even the correct length, right? And you really like to pick all sets of points you can have, it's only a few, and make sort of a lasso and move that around. I guess that would give a speed of another factor of 5,000 or something. And then on the other hand, I found in this sequence you can see triangular grid order 31, 1848 curves, which is nice to look at. You need a fast PDF view. Acrobat Read doesn't cut it. Takes like half an hour. It's nice to see. But what if I find like 10,000 shapes? Even I wouldn't look at that. Right? So that's what I've done. 2 months of hard work, and I got a T-shirt. Gospel wants one. So it cannot be too ugly. And there's another thing which I cannot show you now. All these tiles, every one of them, corresponds to a complex numeration system, as I have said.
Like the terdragon. The same ID than the terdragon. The same ID as for the terdragon.
ID? What's
Idea.
Yeah, but you have to choose, well, you can sort of reassemble it. Here you have to choose a numeration system. This is order 13. 1, 2, 3, 4, 5, 6 digits, and we have another 1, 2, 3, 4, 5, 6 digits. And the self-similarity means you can split that one up in 13 little stars, which you can almost see here. It's a completely different approach, and there's as well literature about which I as well totally fail to understand. And yeah, I think I just stop here and ask for your question.
Is that PDF file like on your website? So
I will do so. I have, okay, very shortly, these are not hyperlinks, so you have to write it down. Because I didn't want, there will be lots of TMP minus extra. I will link them from, this is my domain. I link them from there, all the PDF. Please, if you look at them, just download the whole things, because I pay for bandwidth. Download them, keep them, and don't, they're big files. Very big files, for example, one take picture, look at this guy here. This tag picture, I actually do a graphics and a string substitution engine. And this tag picture is one page, it's 30 megabyte. When text says, sorry, you cannot do that. And then you use Lua tag and be happy. It blows up to 2 gigabytes and gives you a PDF of, I don't know, big. And that's why you need a fast reader.
Is it not by definition very compressible?
It's by definition, yeah, if you, that else is good. Well, cut and paste this, then it's 50 bytes. But if you try this with JPEG,
Or you just like run PostScript commands yourself and
yeah, and then you wait for it. Then send it to your printer a month later, you have it.
The non-zero term thing,
Yeah.
is that's the one below that. Is that not contradicted by the Peano term?
Yeah, I missed this. I don't find these. These use at least 2 symbols. These are actually, this is even more complicated. Okay, I actually lied. I didn't miss it. I explain how I lied. Order 9 gives me that curve. Right? I find this one. Now, this would look ugly, just like a piece of grid. So I round the corners off to make it better visible. Lots of authors do this. But many, or all, seem to miss that if you do the round off to the extreme, you get very good. But I will never find this. I never find the H-dragon. I could build it in, but I'm tired of doing that. 2 symbols, it's actually more nasty than it sounds. But more questions.
So you mentioned that you've sort of got no hope on how to prove these 5 conditions, or rather, you were not able to. Do you have a promising lead on it, or anything? Like, is there any one of these that you suspect is easier to prove than the
I
other?
can see some interconnection, but there's always big missing pieces. Like, this has to be true for the tile to be sensibly defined in a way. And I have idea, if you have a non-zero turn, a net turn, right? Then it's all words and words finer and finer. But these are just ideas. How do I write it down? I can do it. I just simply can. Yeah, otherwise, I would have put the archive preprint out a long time ago, because it is really sad. These things are sitting in my file system and nobody sees them.
Thank you.
Right, yeah.
Jörg, I think there are other graphical representations of file systems. Instead of
IFS, you can always do IFS, right? You can do the numeration system side. You can do this as IFS. Right? You have a common turn and offset by the digits. That's on 1-to-1 with IFS. And I'm pretty sure, following Knut and Davis, that you can do, for example, if you want an IFS for that. Oh, let's take this here. You draw these lozenges around and start with a sort of unit lozenge, and then a lozenge, and that would work. I didn't try it. First, I must.
my idea was just that you could, as you have from many systems like this,
Yeah.
you could make just a little correspondence between the shape given by this representation, the shape given by this, or something else.
I spent many nights putting these things in some shape and form. Even they're selecting these colors to be different and printable on papers. Not nice work. Putting the line width here so you can still look at it. I can. It doesn't have to. This is looking somewhat finished, and same happens in the PDF. So I invest as much work that I say I stop there.
Have you put over characteristics of all those systems into?
Yeah, a text file. You can just download the tiny text files, and you get all these layers.
I mean, in the encyclopedia. Did you?
I do not want to do that much damage to the OES.
Oh. But
no.
Neil will tell you if your sequence is well defined.
Yeah.
Refers to over.
I put in like 2. I think I put in the 0-1 sequence for at least one or both of these dragons for the for this guy, because it is only 0, 1, and for